Welcome here. Today we will discuss some other analysis tools that we use in statistics and probability analysis. One of them is the covariance, and the second one is correlation and independence. So we will discuss this in detail. So first one is the covariance. So if you have two random variables, the covariance of two random variables tells you how much difference between these two numbers, random numbers. So what is the variation between them? So that's why we call it as a covariance. So it is the mathematical representation is as you use capital COV, and in square bracket you put those two random variables, that is x and y, that is equal to expected value of x minus mu of x times y minus mu of y. So this term actually tells you that what is the tell you about the variation between two random variables, that is x and y. So it's used a lot when we do analysis. Now for example, we can calculate the variance. Yeah, this is an example, and you easily calculate the variance. Okay, so we move to next definition, and this is correlation. So the difference between covariance and correlation is that this correlation actually tells you the relation between two variables. Here we have another definition that we relate covariance and correlation using a correlation coefficient. So what is correlation coefficient? Actually, correlation coefficient tells you how two random variables behave in terms of variance or relation. So what is the behavior of two random variables? So that's why we use this coefficient, and this is known as correlation coefficient. And actually this correlation coefficient actually has no unit. Okay, so this is a ratio actually, and this is equal to covariance divided by product of the partial variances of random variables x and y. For example, to understand how correlation variable works here, look here, we have two random variables x and y. So look here, if we have a negative correlation coefficient, so this means that they are moving opposite directions. If we have positive correlation coefficient, this means that they move in same direction. So look here, they have a linear relation. Here they have opposite relation. So negative tells you they have opposite relation, positive tells you that they have same relation. It depends upon the coefficient how strong it is. Okay, so if it is 0, so this means that there's no relation exists between random variable x and y. Now there's a theorem, and a theorem says that if we have a random variable x hat that has a linear relation that is represented by a scalar multiplication of a random variable plus a vice parameter add to it, there's similarly we have a y hat that is scalar c multiplied with the random variable y plus d as a base. If you have this phenomena, so what is the relation you get in terms of covariance and correlation coefficient? So if you have a correlation coefficient of x, it is equal to the correlation coefficient of x hat. So this means that they will follow the linearity. So it doesn't mean if you add a constant or multiply a constant, correlation coefficient remains same. But in terms of covariance, actually you know that if you look at the formula, so from formula you know that it is actually multiplied with the product of a and c, that is multiplied with the random variable. Now there's another theorem, and it tells you the what type of values you get in terms of correlation coefficient. So correlation coefficient is between -1 and 1. So if it is towards the negative side, so this means that the relation between x and y is in opposite or in reciprocal form. If it is 1, so this means that they are moving in same direction or have the same relation. If it is 0, so there is no relation between x and y. Now there is a theorem that can prove this. So the important theorem that is coming to understand the concept, for example, to analyze the concept here, we say that if y and x has some relation, okay, to explain this correlation coefficient in detail, assume that y is equal to ax plus b. Okay, now if we have a correlation is equal to -1, so this means that a is a negative one. So this means that if y moves in x direction, y moves in a particular direction, for example, say a, and x move in negative of a. Okay, so that's why a is less than. So they have reciprocal relation. If a equal to 0, so there's no relation between x and y. If a is 1, the correlation coefficient is 1, so in that case x and y has same movement in same direction, or in other words, they have a linear relation, okay, with same direction. They have a reciprocal relation here if correlation is negative. So these are some common examples to understand the correlation coefficient, and it's very important uh, what your analysis tool that we use for analyzing the random variables in different application of engineering. And we say that for example, if x is a student height and y is student weight, so we can say that we can have relation between 0 and 1, because if as height increases, your weight also increases. But if x is the distance of a cellular phone from the nearest base station and y is the power of the receiver signal at the cellular phone, so we know that if we have distance increase, power will reduce. If distance will reduce, power will increase. So in that case, we have opposite relation. So we have correlation coefficient between -1 and 0. Again, if we assume that x is the temperature of resistor measured in degree Celsius and y is the temperature of the same resistor measured in Kelvin, we have correlation coefficient equal to 1, because they represent the same thing. Another example, if x is the gain of electrical circuit measured in decibel and y is the attenuation measured in decibel, then the correlation coefficient -1, because attenuation and power or gain of the circuit is opposite relation, has opposite relation. So that's why correlation coefficient is -1. Last example to understand this, and this is very important, if x is a telephone number of a cellular phone and y is the social security number of the phone's owner, so there's no relation between security number and the telephone, or in other words, if you have a national ID card number and the cellular phone, there's no relation between them. You can't extract any information that relates the national ID card number with the telephone number. So that's why the correlation coefficient is 0. Okay, so from here, from these examples, we understand that correlation coefficient tell us how two random variables relate with each other. Now the other concept with correlation, covariance tell you the variation. Correlation tell you how this variation works. There's another term that we can use is known as correlation, that tells the relation between x and y, and this is represented by r with subscript x comma y. This is equal to expected value of x and y. Now this is a theorem, and that relates correlation coefficients and correlation with covariances, and that says the variance of x and y is equal to correlation minus mean value. Similarly, variance of x plus y is equal to variance of x plus variance 2 times covariance of x and y. If x and y are equal, in that case covariance is equal to variance of x, that is equal to variance of Why? Because covariance of xy becomes 0 if they are equal. But correlation in that case becomes expected value of x square or expected value of y square. So this is the theorem that relates these properties, and we use this for application purposes. Now this is the proof of that. Now this is an example that you can do to calculate the correlation covariance. So if we do it, so we have to, for correlation we have to find the expected value x and y. For covariance we have to put the formula and we easily calculate it. So I leave this to you guys to calculate it, apply the formula. So orthogonal random variable is defined where we have x and y and their correlation is 0. So I stop here for this video and we'll continue in next video. Thank you.